Hello everybody, welcome back to this channel. So today we're going to have a look at the Fourier series, which is a very important topic in certain research areas, and also in general in engineering we have a lot of scenarios we need the Fourier series, especially in the research area I'm working in, the power electronics. We have the switching waveforms and we get useful either DC or sinusoidal from those switching waveforms. And the Fourier series plays a very important role. So as always, I'm going to put the link to the Google Colab notes in the description down below. And if you have any comments, feel free to leave in the comment area. And today we're going to have three topics. So the first topic is just from very basic, because some students may not recall the periodic function. So we start with the periodic functions and introduce the Fourier series, and then the second one would be how we determine the Fourier series. So we're going to have an example on that. And the third one is we're going to look at alternative forms, especially the complex form of the Fourier series, which not included in the text. I think is very important for you to know. And also I have an example on that. So today we probably will need five video clips to cover this lecture. So let's start looking at start with the periodic function, and let's see if we have a function ft is periodic if let's see ft plus or minus a capital T is equal to ft. And in this capital T would be called, capital T is called the period, and the smallest positive T that satisfies this equation ft plus or minus equal to ft is called the fundamental period. And most cases we talk about the period, we talk about fundamental period, the fundamental period. And there are numerous periodic functions there. And I have a Python in the Google Colab notes. I plotted a few. Let's see, this one here, the first one, the triangular waveform, and this one repeat every T, capital T, right? This capital T could be anything. And if you have very high frequency, and especially in power electronics, you can use a carrier for triangular. And if you're switching at 10 kilohertz, that means each period is only 100 microseconds. And this is sawtooth waveform, another form of periodic. This one here. Oh, I need to move up a little. So I just want to minimize the header. And if this one here is a square waveform, so that goes the positive and negative have 50% of what we call duty ratio. And so the period is apparently the waveform repeats itself every T, right? That amount of time, that's fundamental period. And we rarely see this this waveform also repeat every 2 T's, right? So that's not a fundamental period. For the rectangular pulse waveform, so the pulse depends on the application. The pulse could be very narrow or could be having higher duty ratios. And this is the examples of the periodic functions. If we have the periodic function, another thing I want to include is the if we have a T, the fundamental frequency, the omega is going to be equal to 2 pi. If we have the fundamental period defined, the frequency omega is going to be equal to 2 pi over T. This is the radian per second, and called the fundamental frequency. Fundamental angular frequency. And also, if you use hertz, and f is going to be 1 over t. These are a few things we should be very clear about. The hertz is 1 over second, and this is the fundamental frequency. So it is all very windy outside, so you may hear some background noise. I'm sorry about that. And so if the function ft is periodic, then we can write this in the Fourier series. F can be expressed in Fourier series, and this is a new term. And basically a sum of the DC component and the sinusoidal components. And in ft going to be equal to, let's see, call a0 plus the sum of a sub n times the cosine n omega t. Omega is the angular fundamental frequency, plus b sub n times the sine n omega t. And n can go from 1 to infinity. And a0 is called the DC component. And an and bn for n is equal to 1 to to infinity are the Fourier coefficients. For the AC terms, and sometimes we call A the Fourier coefficients for the cosine terms, and the Bn is Fourier coefficients for the sine terms. And so for this Fourier series to be convergent, and there are certain mathematical the condition for the ft, and we're not quite concerned with that, because for any practical waveforms we saw we can generate physically, they always have this convergent Fourier series. So we don't really worry about that. And basically you need to have a finite number of the discontinuous points in the ft in per fundamental period. I mean, almost like there's no waveform we really have that in practical waveform we don't really have anything that do not satisfy that condition. And also there is the integration of ft in the fundamental period had to be finite. Things like that. We don't really worry about those conditions. So we're not going into the detail, mathematically rigorous details in that area. And then next video clip, I'm going to talk about how we're going to determine these Fourier coefficients an and bn, and also DC component a sub 0, right? And because that's important, and once you know these, you know what the Fourier series really is, and you can use that Fourier series. You know the different components, and also we talk about the filters, right? So you know how each component going to be attenuated by the filter. So this is really the foundation of log analysis you're gonna do in the signal and system stuff. We're not going into detail after we introduce this, but this is really a topic you should know very well. I'll see you in the next video clip.